Hello everyone and welcome to our webinar today. My name is Paul Bemis. I'm the President of Applied Math Modeling. And today we're going to be reviewing some material that I have done before. I think the last time I did it was with Magnus Herlin, who we've worked together on design optimization before for airflow, and I'll reference some of his material here in a moment. So this is about optimal design in operation. And before we get started, for those of you who don't know me, most of you do, I'm the President of Applied Math Modeling. We're responsible for the CoolSim data center modeling application. It is a SaaS-based delivery system. We have backgrounds in CFD. I was with Fluent for many years as the head of their product development and product management organization, as well as with Ansys. We also use their engines to solve. So CoolSim is effectively a user interface on Fluent, which is now an Ansys product. So we're using state-of-the-art CFD behind CoolSim. CoolSim just is focused on data center specific. It is what we call an application-specific tool. So it's focused on data center analysis, but does run Fluent in the background, and that's how we roll. So quick overview. Every data center has an optimal design operating point. This is where energy is minimized for the operation of the data center. Knowing where this point is important, and we're going to take a look at it in some detail here. Now, I need to preface this by saying data centers are ever-changing. They're actually transient environments. In other words, they're all changing all the time. Equipment's going in, equipment's going out. So the data center is a very dynamic place, and we're going to be modeling it as a steady-state environment. And the reason you do that is to give you more information than you have without doing that. Specifically, you need to understand where that optimal operating point is so that you can get as close to it as possible for optimization of energy. And with the cost of energy the way it is, this is becoming more important every day. So today we're going to determine or do some analysis to find out where that point is for a given data center. Okay. So we're going to build the data center in CoolSim, perform variations to optimize its design. And the way you do that for air-cooled data centers, which they all are still, is adjust the airflow balance, then adjust the supply air temp, and then drive up these two parameters called RTI and RCI. Now, for those of you who have been through the Data Center Energy Practitioners program, which is a DOE program, you will recognize that, You will recognize those parameters. I'm going to go over them a little bit for those of you who don't. If you haven't taken that course, I'd recommend you take it. It's a good one. It's sponsored by the Department of Energy. It's called the Data Center Energy Practitioners Program. And some of these slides are from that program. The last time, as I mentioned, I did this, I believe I did it with Magnus Herlin. So a lot of this stuff comes right out of DCEP training. So let me first talk about a couple of terms, the term recirculation and bypass. Each piece of equipment in a data center, each rack, has an optimal amount of air that goes through it. Now, these are dynamic devices as well, actually. These have variable speed fans in them these days. So knowing the amount of air that goes through these devices is not always evident and obvious, but there is a certain minimum that is required to satisfy the requirements of an IT rack, and we'll talk about that a little bit more in a moment. But if there's not enough available air, cool air coming in, and the rack is just sitting there, it will recirculate on itself. So recirculation is the idea of a rack, an equipment rack, breathing its own exhaust, in a sense, right? It's just wrapping around in a circle, and you see this a lot in CFD output. The other problem that is common is bypass, where you've got too much air coming in, and it goes right by the equipment and goes out the other side. This causes problems as well. So a different kind of problem than this one over here, but both of them are bad. What you'd like is a perfect amount of air. If you could set up a data center with the cooling unit right in front of the equipment rack so that goes from here to there right straight through it, that would be great. There are designs that attempt to do that. Many of them do it on the backside. So there's a heat exchanger that sits back here and absorbs the heat on the way out. That's a method that's used, rack level cooling. But in any case, you want the right amount of air. And so the terms recirculation and bypass airflow are terms that I will be using. So air management is providing the right amount of air for the servers, and that relates to energy because delivering cold air is expensive, and then that relates to capital because if you don't set it up correctly, you will shorten the life cycle of the cooling equipment. So it reduces capital investments for replacement. You can get more life out of them. So air management is key for data centers. It is how we cool them today. There's a lot of debate about going to liquid cooling. We have been there before in electronics packaging. I remember it. I'm old enough to remember the liquid cool craze, as some of you in the audience are. And we'll probably go back to liquid. But even in the cases where we have liquid cooling, there's still residual heat that needs to be removed from the data center, and that's done through air cooling. So data centers at national computer sites that I've worked on are related to residual air movement and cooling even after the liquid has been transferred through the equipment because the liquid cooling is not perfect and there's residual heat. So air cooling and air management is going to continue to be there even if, in my humble opinion, we move to a full liquid. So air management goals is to always give the highest supply air temp you possibly can and the lowest airflow rate that is possible and still satisfy the needs of the servers. You want to make sure that this is sufficient, that it's low enough but sufficient, and that gives better chiller efficiency, better reduced fan energy, makes the servers happy, and enhances economization. If there's economizers being used, it will enhance economizers. So there are some metrics that were developed for this. This is again part of the work that Magnus usually does in the DCEP training, and they're called RTI and RCI, and I always like these because they are metrics that you can use to drive parameter optimization or design optimization. The first one's called RTI. It's a return temperature index. I tend to refer to it as a room thermal index, but it's a return temperature index. And I always think about it from a flow point of view. So it is in the denominator, the air handler flow rate, in the numerator, it's the rack flow rate. So the racks will require a certain amount of capacity, certain amount of air. And then the air handles will deliver a certain amount. And you want those to be balanced. In a perfect world, the relationship there would be 1-to-1. And then they multiply it by 100 to give you a whole number. But typically that denominator is bigger than the numerator because you're supplying more air than necessary because it's not an efficient environment and you're trying to compensate for that. So 100% is good. If you're greater than 100%, you're going to get rack recirculation. That means that you're not giving it enough air. The denominator is too small up here, and that drives the RTI greater than 100%. That's bad. So you want it less than or equal to 100, never greater, and you'd like it in the 90s is where you'd like it. Okay, so that's RTI. That is the basic fundamental parameter that I always look at in a data center. Long before this index came along, we had a similar one for CoolSim where we did this ratio. I can't remember what we called it. But we were always looking at what the rack needs in total compared to what the air handlers are supplying in total. That balance is important because if you overdrive the air, you're going to reduce the energy efficiency and life of the equipment. If you underdrive the air, then the racks are going to recirculate on themselves and you're going to have hot spots. Very straightforward. This one is a little more subtle. This is RCI high and low. This really is how many hotspots are there in the data center? So this is specific to the ASHRAE thermal guidelines. It's really a compliance metric. And we also have a compliance plot that I'm going to show you in CoolSim that does the same thing as this, but it does it visually. This is numeric. It is of all of the temperature situations, the total over temperature situations, how many of them are there? It's basically a ratio of the number of hotspots in the data center. And that's the best way to think about it. We always do it based on recommended range, the ASHRAE recommended range, which is 64.4 to 80.6 Fahrenheit. And you want, again, this to be in the range of 95 to 100. Now, some will say, well, that suggests there are hotspots. Yes, but at least you know where the edge of it is. You want to be on that edge of good. You want to be on that edge of, I don't have too many hotspots, or if I turn temp up just a little bit more, I know I'm going to get some. That's the optimal point. You need to know where that edge is. RCI low is not used as much because this is how many are under this range. I mean, data centers today that are showing blue, I'll show you this in a moment, but data centers today that are supplying lower than 64.4 or 60 degrees, I mean, allowable 60, electronics equipment doesn't degrade with temperature. You know, you can run it cold, but it's a thermodynamic train wreck with respect to energy. In other words, you're using an awful lot of energy to get that cold air. So the question becomes, why are you running that cold? Whenever I am in a data center and they're running that cold, I know that they're paying a lot more for energy than they should be, and the data center is not optimized. So for creating a CFD model, we first build it in CoolSim. We avoid small details because they won't affect the overall outcome. You need to be careful not to over detail. It is not a CAD system, it's a modeling system. We're looking for big parameter variation. We're looking for the most influential parameters, the dominant parameters like placement of things like cooling units and racks and equipment in the room. Height of the room, we need the volume of the room, of course, so plenum height, ceiling height, return height, placement of racks. Those are the important things. This is the set of important things. I find users get wrapped around the axle a little bit on this work in CoolSim because they over detail the model in the case that it might matter. That's kind of the argument. I'm going to do it just in case, but often it doesn't. The way to find that out is to first model it without it, and then if you want to know if the detail is affecting the design, put the detail in and model it again and see if the parameters change. I mean, there was someone who famously said a model should be as simple as possible and not simpler. You should try to get it down to the minimum dominant parameters that are driving the design. This is true of any design, by the way. It could be automotive, could be data center, it could be anything. Find the dominant parameters and focus on those. That's where you'll get your highest return. And we typically start with watts per rack. This is another one. How much detail should I put in the rack? Well, you can always add detail later. Start with average because that'll tell you an awful lot about the general flow in the room and what's going on in the room, and you can always go in and tighten up the model later. But over-designing a model from terms of detail early on slows you down and doesn't allow you to get your arms around what's going on in that data center in terms of understanding how those parameters affect the overall design. The other thing about average watts is oftentimes we don't know more than this, right? Because unless you go in and do a physical inventory, you don't know what the distribution is. And even if you do physical inventory, it's difficult sometimes to determine what the allocation of wattage is in the rack because you have to instrument each of the servers. You can guess if you like. Some providers like to say, well, it's 60% of total nameplate. So you take the worst case condition of the server and then you multiply it times 60% and you use that. That's still a guess. So the best thing to do is know what the watts are going into the rack, assume that it's spread across the rack evenly first pass, and start there. You can always go higher later. And then use that model to determine optimal operating point and then go in and tighten it up if you need to. Because the optimal operating point is more general. It's dealing with air handler total airflow. Okay. The governing equation for all of this, by the way, this is the convective heat transfer equation. So heat transfer is equal to mass flow rate times specific heat, in this case of air, or density times specific heat times delta T. This is delta T is the return supply delta. This is, of all these devices, it's the same equation for servers as it is for cooling units. And what you're hoping to do is get the delta T's to be the same on the cooling units as they are in average of the racks. You want to balance the heat transfer in the room. Okay. So the optimization steps are as follows. Adjust first the airflow coming from the air handler units to match that of the demand of the racks. So that's again the RTI parameter, and you want to drive it towards 100% until the racks start to show a little bit of well, either you get it to 100% or the racks start to show some bleeding on the edges. I'll show you that in a moment. Or RCI begins to decline from 100%, whichever happens first. They're correlated, by the way. And implement air management is necessary. I mean, this tells you a lot by itself. Just taking the total amount of air that's going into the room and starting to decline it will show you where the room has trouble, where the environment is struggling to get air to where it needs to go. It's always the case. So this exercise alone tells you an awful lot about what you need to do in the data center to make it healthy. And then once you've done that, you have the opportunity to drive up supply air temp. And you want to drive up supply air temp until you start to see RCI come down a bit, and you're going to get savings on that. This is, by the way, a rule of thumb that's in the literature. The basic thought here is that, or the conclusion here is that for every 1.8 degree Fahrenheit increase in supply air temp, you get about a 3.5% increase in mechanical energy efficiency. Now, I'm going to hesitate right there because this is this is a rule of thumb, and I don't like rules of thumb, and it's linear, and I don't like things that are linear because, of course, CFD is highly nonlinear, and I live in a very nonlinear world. So this is coarse, but it serves a purpose for first pass analysis, and the ability to model this behavior in mathematics is clear and evident in this work going on in this space. We're going to talk about that in a moment, and show you how we can do much better than just that. But remembering this ratio is important. You can think of it in C as well. It's a little easier in C because for every degree C, you get about 1% efficiency improvement. It's a little easier than F. But that's one that I use quite a bit, and it's useful. I'm going to use it here today. So here's a plot, a graph of how this all works together. So as you drive our RTI up, so here remember that the air supply is in the denominator, and the rack requirement is in the numerator of this relationship. So as I reduce the air handler volume, that ratio increases until it gets to a certain point where it'll start to show hotspots. Now, the reason it's showing hotspots is because we're starving it for air effectively, right? So the racks will begin to recirculate on themselves, breathing their exhaust in, unless there's containment in place. If there's containment in place, it gets worse. So we won't talk about containment for a moment. We'll talk about a freestanding data center where the exhaust can be drawn into the intake. Now you don't want to go until RTI goes beyond 100%, because now you're literally starving the situation. You're not providing it enough air, and it has no choice but to recirculate on itself. But as you go up, you'll get to a point where RCI begins to decline. And the optimal point is really right about there. You don't want it to decline, or RTI gets to 100, you can stop there too. RTI typically won't get to 100 because you're going to need a little extra air because there's leakage in the system, and it's not going to be perfect. So drive RTI up into the 90s would be my advice, and get it close, and then begin to increase your supply air temp. So, okay. So we're going to experiment with this today. We're going to take a look at a data center. This is a customer's data center that said it was okay to use it. And they were basically asking me, or wanting to know, what the economic benefit was of adding cold aisle containment. You'll find there's a lot. People will ask you, as practitioners, they'll ask you, what's the benefit of this, or what's the benefit of that? And they'll want you to show some economics on it. So we're going to just show you how to do that, at least first pass analysis of how to do that today. So here's the base model. It's nothing very complicated. This is what we call a convective return, naturally convective return data center. You see on the perimeter, you have these units here, cooling units. These are air handlers. These are fan coils. Downflow in this case, raised floor data center, perforated tiles here in front of the servers. It's lined up perfectly in terms of hot aisle, cold aisle. The hot aisles are here. The arrows indicate airflow direction, so you can see it's cold here and hot over here, and very natural. The only reason there's partitions around this is probably a colo. So these are screens. They have a high % open area, so they're not enclosed. This is all open from an airflow point of view. Very common, and PDUs are in red around the perimeter. Very common data center. That's not unusual here. Now, in CoolSim, there is the ability to open this up and to look at results. So I'm going to pop a display here and drag it over. So this is the output of that analysis. This is how it comes out of CoolSim. This is a report that you get back, now available. I can actually share this with you. So I'm going to copy this, and I'm going to try to paste it into the chat window. Let's see if I can do that. Sharing. Where's chat? Just bear with me a second. I'll try to find it. Yeah, there it is. So I'm going to paste into the chat window that URL. And this is a new feature in CoolSim, so I'm showing off a little bit here. We're able to share the entire output report via URL. Really nice. So you can click on that yourself and kind of follow along with me if you want. Or you can just watch. So we break this down into several sections. Now in this base data center, you see here under data center description, it is a 6,000 square foot area, and we have a total flow through the crack units of 211. 211,880. Okay. Now the racks want 140,594. Those were set up using average watts per rack, and we're set up with a delta T of 30 degrees Fahrenheit and a mass flow rate of about 125 per kW. That stuff's all part of CoolSim. You just put in the kW, it'll calculate it for you. You can set the delta T if you like. We use 30 today as an average. You can use whatever you like. You can use 25, 20, it's up to you. The older designs, if it's older equipment, it's closer to 20. If it's newer equipment, it's closer to 30. 25, I think, is the default at CoolSim. We keep rising it or increasing it because these things, the heat exchange is getting better on these devices. The total load in the room, 966. So let's just see, let's take a look. Over here are the 3D files, and the one in particular is the ASHRAE recommended range right here. This is my go, no-go gauge. Okay, this is a visual representation of RCI high, right? Because it's a conformance plot. It is on the low side 64.4, on the high side 80.6, and you can see that we've set that data center up so it's just starting to bleed, what I call bleed. We call these Visine charts. For those of you who grew up in the United States, you would know what that is because Visine used to sell advertising for getting the red out of your eyes. And bloodshot eyes, you use Visine, and we used to call these Visine charts because we were trying to get the red out. So that's the joke you probably won't get unless you grew up in America. But yeah, this one's okay. Read along these sections, this isn't unusual because what's happening here is that's right on the edge. The chances are that's probably okay because you're not going to put servers in that section anyway. Most people who are doing data centers understand that that last tile is problematic. It's getting a lot of velocity from the crack unit here under the floor, so the perforated tile is not performing really well right there due to high velocity underneath it, and Mr. Bernoulli is causing pressure to be low right there due to high velocity. And so edges are always problematic. Over here, you know, there's a tile missing, so there's that. You could fix this room a little better so that one doesn't pop out so badly. But in general, this one's optimized. In other words, this is as good as you're going to get for this kind of data center that is what we call naturally convective, because it is going to do some recirculating back on itself. You can see that visually down here in the path line plots if you want. If we take a look at, for example, path lines from floor tiles, you'll see some recirculation. Path lines I find to be useful to understand where the air is flowing in the room. So here we have the air coming up and recirculating back into the cooling units. This is generally bad. This is recirculation, as I defined early on, and you're seeing it visually. What's happening here is the air is coming out of these perforated tiles and not going through the rack. It's going right back to the cooling unit. This is bad because it reduces the efficiency of this cooling unit. Remember, you want as big a delta T as you can get on these devices. That's what makes them happy. That's what reduces the energy consumption of the chiller. And without having a high return temp, you're not going to keep the energy down. So this is the basic problem here. You can see this tile is not delivering much either. There are many plots and graphs. I don't want to go into an exhaustive look here of CoolSim. It has a lot to look at, though. That's why I handed it to you so you could see it. This is a plot right here of flow rate per tile, and you're going to see that the tile near that edge where that rack is having trouble. So let me just, this is a Y key. We support keystrokes, so Y, N takes off perspective. And you can see that one that we were looking at earlier where it's bleeding is right here. Is it right here? Any of these edges. There's another set right there. These are really low, and it's because they're close to the edge and causing problems. Okay, some other low ones over here. So you get a variation in floor performance, tile performance based on location. This is normal. The pressure under the floor is not uniform, and so the flow rates of the tiles are going to vary by some factor. In this case, we're going from 910 to 1300. So we're seeing a variation of about 30% roughly. Now, back to this section, there's an energy report here as well that we calculate. And you see here I'm calculating dollars. I'm also calculating RCI high, RCI low, and RTI. Now my RTI is only 66. That's pretty poor. That means I'm over-delivering, which is exactly what you're seeing up here. You see we're delivering to 11, we only need 140. And the reason we're over-delivering is because we have no choice, that we can't control that airflow. It's recirculating on itself and coming out of those tiles right back to the crack units. Where you have also rack recirculation going on. You can see that as well in the other plot that shows path lines from racks and PDUs. That's this one. And you can see here that in some cases these racks are just going to recirculate a little bit on themselves, causing hotspots to occur. Sometimes it's around the edges. You see it right here. It's going right around the outside and not over the top, but around the outside and getting sucked into the intake. So it's breathing its own exhaust. Those are colored by temperature. And you can see quite a bit of recirculation, particularly right there on that top edge, which is where we were seeing the hotspot earlier. So this allows you to look at your data center and see where the problems exist using these graphs, plots. This is automatic output. I didn't do anything unique here. This is exactly what comes out of CoolSim. I did up front put in a COP. So let's talk about COP a little bit. I put in a COP of 2.8. COP is coefficient of performance. It is a user input right now in CoolSim. Now that will change with time. We're going to be calculating this for you, but at the moment it is a user input. And we'll talk more about that in the energy section. We calculate PUE based on that, and then DCIE, which isn't used as much. Most people use PUE. DCIE is just the inverse of this as a fraction or a percentage. I'm sorry, as a percentage. RTI 66. RCI, notice it's 90. We've got some hotspots there, and I just showed them to you in the compliance plot earlier. RCI is not a problem. We're not too cold. Total facility power, 1640. Okay, so that's kind of an interesting number. That's the total facility power required to operate. That includes the rack power, which is 966 in this case, plus the energy required to dump that heat to the outside atmosphere, assuming the overall data center has a coefficient of performance of 2.8. Now, for those of you who are following ASHRAE, and I think Henry Amistadi might be with us, we worked together on this. He's on the 90.4 committee, and you know, there's work going on to turn this number right here, COP, into something called MLC, mechanical load component. They actually use it as an inverse of COP, so it's a fraction. But nonetheless, it is the same kind of thing. It is the measurement, or in his case, the prediction of the total energy required to operate the data center compared to the load in the data center, IT load, really thermal load. So we have that, and then all these other reports that go with it, including crack. Now, crack's important. We call it a crack. It's general. It could be air handler. We've got the supply air temp set at 68 in order to make this data center work. That's a little cold. I'd like it to be warmer than that. We calculate the return air temps and we average it. So we've got a delta T here that's not great. You'd like that delta T to be exactly what it is for the racks. And you can see here that we're operating with a delta T of about 14, 15 degrees there. Yep. So, okay. So that's where we are. I wanted to show you that on this data center. Here is it in spreadsheet form. The rack is requiring 141. Every air handler is 18K in this case. The average power consumption for the fan for 18K is 11.2 kilowatts. So you just take the horsepower and convert it to kilowatts. We've got some extra load in the room of 3 kW. I'm only concerned about right now PDU load. ASHRAE 90.4 is getting into more than just that. It's every single load in the room, lights and any other heaters, block heaters for diesel generators. I mean, all kinds of things go into the total load. I've got my temperature separation here, supply air temp, return air temp coming from the CoolSim output report. And these calculations I did in a spreadsheet. Now, I tried to attach the spreadsheet earlier. I'm going to try to do that again. It gave me a hard time about that. Said it couldn't do it. If any of you want the spreadsheet that I've used here, send me a note and I'll try to share that with you. I will share that with you. I'll try to do it again here today. Handouts. Here we go. So choose a file. Let me see if I can choose that again. I was thinking maybe it wouldn't let me do it during, yeah, it's throwing an error. We apologize, but the error has been occurred. Sorry about that. GoToWebinar doesn't work really well on file transfer, apparently. But this is a very simple calculation to do. So 966 is the total load. PDU and UPS loads are 16.1. This is an input, user input of 2.8. Total airflow, 211,880. This came from the, of course, the CFD output report. Total energy required for airflow is just, you know, the total airflow times the load per air handler for 134. So all I did is sum these because I'm operating at full capacity at the moment. So I'm operating with these things on full tilt, full blast for the most part. So that means the total energy for cooling data is 533. Now, just a moment on this calculation right here. Remember that the reason it's 533 is you've got to dump the heat. This is the energy required to dump the heat, 533. And it is the total amount of energy in the room, which would be 966 plus 16, plus the energy for airflow divided by the COP, because you're dumping that heat. And then you have to also add in the energy required for airflow one more time. It's important to remember that. You put an air handler in a room, you have to pay for it twice. The first time you pay for it is in the energy required to spin the fan. The second time you pay for it is, at the end of the day, that energy turns into heat and has to be rejected by the heat rejection device. So you pay for fans twice, once to power them, and then once to dump the heat that comes from the fact that they generate heat. At the end of the day. So a little bit of thermodynamics there. And then down here is 1649. It's interesting to compare these two numbers. That's not a great relationship. So 966 is your total IT load. That's what you're really interested in from a productivity point of view. This is the one that's most important. But it's taken 533 to get that heat out of the room. So effectively, for every kilowatt that we're putting into the room for IT load, it's taking half a kilowatt to get it back out of the room. Not a great relationship reflected in the PUE of 168. Now, if that PUE were 2.0, for example, it would be a 1-to-1 ratio. In other words, for every kilowatt that you put in the room for IT, you need another kilowatt to get that of energy to get it back out. So that's kind of an interesting way to think about PUE. We're not quite that bad. We're at 168. room for improvement. So here's optimized design. This is just cold aisle containment, not too complicated here. All you need to do is put the containment in place. I want to remind CoolSim users that it's not necessary to, on the containment side, to make small pieces of the containment. You can take one long piece of containment and slice right through the racks, and then do another one on the other side, put the top and the ends on it, and then group it, and then clone it. Clone is copy with offset. And so I just, for my CoolSim users, I often see people trying to make little small pieces in here to contain, and you don't need to do that. You can slice right through a rack. A rack is nothing but a block with an inlet and an outlet on it, and a function that we have to determine the heat transfer associated with the inlet and outlet. So it's not a hollow block, it's a solid block. So slicing right through it is fine as long as you don't interrupt the inlet and outlet, and then you can group the containment and clone it. So containment is very quick and easy in CoolSim. You want to set the leakages on these. Racks do leak. Containment leaks. So what I tend to do is put a little bit of leakage right along this edge right here, because that's typically where they leak. I don't leak it on the top, and I don't leak it on the ends. I leak it right where it intersects with the racks at about 5% leakage. And that gives me a parameter to represent something closer to reality than zero. So you have to assume some kind of leakage. Now I just opened this one again. I'll paste this one into the share area as well. Let's see, where'd it go? So let's see, I can chat again, Control V. So I just pasted into the chat window the URL for this data center as well. So again, description of data center is pretty much the same, except we've dropped the total flow through the racks down to 144. And you see the rack requirement is 141. So we're getting really close. That means RTI is going to be closer to 100% right there. And if I go over here again and take a look at our conformance plot, ASHRAE recommended conformance plot, we're doing pretty good now. Now this shouldn't surprise us. We've done containment, right? I mean, containment is pretty mechanically solid. You're going to block any air from leaking around these racks. You see there is a little leakage over here because there is always leakage, and these don't perform well. So you're seeing some leakage in the same sort of areas, but again, I've optimized this data center. I've driven the temperature up as high as I can, and I've driven the RTI up as high as I think is reasonable. And this is an optimized data center. By the way, these corners generally don't matter too much. It's not like you're going to stick high-density servers up there. If you're experienced, you tend to be sensitive about the ends of an aisle anyway. So this one's probably fine in terms of operation. And you notice here we're operating at a supplier temp that's higher as well. Let's take a look at our supplier temp. We're at 71.6. We got a 92.56 return air temp. So now we're up at 31 degrees roughly of return air temp. Much better off. Okay. So, and we're operating at 12,000. So we've reduced the fan requirement from 18 to 12. That's big. Remember that this is a cubic relationship on fan. So as you reduce the CFM on a fan, the power required to drive the fan drops as a cube of the RPM or CFM. So we're gonna gain there. And now let's take a look at our data center energy report. The COP we moved up to 3.16. Now the way I did that was to take the difference in return air temp and divide it by 1.8, because I get 1.8%. I'm using a rule of thumb here again. I get 1.8 for every 1.8 F that we increase the return air temp, we get about 3.5% improvement in COP. So all I did is take the delta T on the return air temp from the earlier run and this run, divided it by 1.8, multiplied that product by 3.5, and increased the 2.8 to 3.16 as a result of that. That's how we did it. Now, there are many of you who say, well, that's pretty rough. Yeah, Henry's probably having a fit because, you know, there's a lot in that right there. I just did a lot, right? I made some pretty big assumptions there. But even if you model a data center distinctly, uniquely, discretely, you're going to end up with an average COP for a calendar year. Remember, these things are not steady state anyway. The COP is going to vary by the hour, depending upon, for example, you've got an outside economizer, depends on outside air temp. It depends on a lot of things. Depends on the cost of electricity as well, by the way. So COP is a number that, for purposes of this analysis, this methodology that I'm teaching you today, is a hand calc. Now, over time, we're going to implement into the software the ability for that to be a machine calc done in CoolSim based on locality and other factors. But it can get complicated because, remember, the pumps are variable speed, the fans are variable speed. Remember that the environment is different for each data center in terms of where it's located. Is there an economizer involved? If so, how's it set up? So this can go down a rabbit hole of complexity for determining what this number is. And that wasn't my intent today. My intent today was to show you methodology related to data center design optimization and not energy prediction. Henry and I have done these analyses before. Him and I we're talking about doing it again. Maybe in the next webinar where we dive into this, maybe we take the same model and dive into it a little deeper and do the real energy analysis based on a location in the United States. And you can do this externally with other programs as well. Certainly the DOE tools and Energy Pro, you can do this kind of work. Design Builder does this kind of work. But we'll also have a certain amount of it built in at some point. So the COP went up to 3.16. And that's because the return air temp increased. And the PUE got better. The RTI is now 98. The RCI high is 96. That's a nice set of parameters. So I'm pretty much optimized right there. I already showed you supply air temp. Supply air temp down here is 71.6. We're able to move it up to. And the whole thing behaves better. Not much to look at on these plots other than because it's contained. So they don't really show you all that much because it's, of course, contained. So the airflow plots aren't that interesting anymore. It's pretty much, you know, it goes in and stops. That's from the supplies. This is the returns here. The returns are a little more interesting because you've got all these path lines coming from the hot side. And you can see they're coming back and they're coming into the returns as they should. And the only problem with a cold aisle contained design is the room is the hot aisle. So for anybody in this room who has to change equipment, they're going to be hanging around 90-something degree temperatures all day long. And it's kind of tough on the human, but, you know, you shouldn't have humans in there. I realize you got to change the equipment, so I know humans are in there, but it is not an office environment, that is for sure. All right, so let's go back to, so what we did here is the rack requirements stayed the same. We were able to drop the total airflow down to 144. We reduced, therefore, the fans by 28%. The fans are cubic in nature, so we got a big savings from fans alone. The fan energy reduced. The fan energy alone dropped by 50 kilowatts, just dropping the fans down by themselves. And we went down to 1359 for total amount of energy required to drive the data center based on our new COP. Fairly reasonable numbers, fairly reasonable representation. It's a little coarse on the energy analysis, but still serves the purpose quite well for most cases. Again, remember, COP is something that you can spend a lot of time on. And at the end of the day, you will use an average annual COP to do these kinds of calcs. And then down here, we have some cost of electricity and annual savings in kilowatts. This is the most important. How much did we save? Here we saved about 300 kilowatts. You can plug in your own numbers for cost of electricity and make some assumptions. My assumptions here were that electricity is constant. It never is. But nonetheless, this will give you the ability to put forward an argument that yes, it does save money, or no, it doesn't save money. By the way, it always will. It's just a question of how much. What generally they're looking for is this kind of return on investment. How long would it take us to cross over and recoup the investment necessary to do the implementation. So at 20 cents a kilowatt hour, annually we're saving, in this case, $500,000 of operating cost, and that's pretty good. So I'm going to open it up for questions if you like. If there are any questions, please type them in or put your hand up. And this is a summary of the process. We built the model. We first reduced the airflow, the total airflow to it by just reducing the amount. You can do this a couple different ways in CoolSim. You can do it by hand, where you just drive the parameters down on the supply side. You can also use a VFD. You can put a sensor under the floor and change the pressure sensor or the temperature sensor so that it delivers less air. Either one works. Either one can be done. And then we used air management techniques to improve the airflow in regions that we had problems. Then we drove up supply air temp. So what you're trying to do is reduce the amount of air. That drops the fan speeds down, saves you money there. By the way, again, that's cubic in its savings. And then we want to drive up supply air temp, which makes the heat rejection system work really well. Remember, if you get that return air temp hot enough, you can use economizers or other methods to dump to the atmosphere without having to go through the compression cycle. That saves a tremendous amount of energy. And yeah, that's a summary. We use CFD modeling to show it. And this is important for those of you who use these tools to be able to take the science of airflow and CFD and match it to an economic question that people will ask you about: how much am I saving as a result of this? Or if I were to design an A-B comparison, how better is B than A? How much savings does it make over what period of time? So with that, I'd like to just open it up for any questions you may have. Again, you can type your questions in, or you can take it offline and ask me later. Here's my email address. I did try to share that little file with you. I don't know why my little file. We apologize, but an error has occurred. But I did give you the URLs. If you want to save those URLs, those will last. Those are permanent. You can share those with others, or saving as a bookmark to be able to view some CoolSim output if you like. And all right, then I think that's good for today. I want to thank you all for attending this webinar. I hope you find them informative. If you have suggestions on how to improve it or topics that you'd like me to cover, please send me a note and I will pick those up in the next webinar. I try to do one of these at least every month. Sometimes it's every other month, but I think it's an important way to help teach you what to do and how to do it. Thanks everyone, and have a good day.